All right, in this next video, we're going to take a look at the next stage of atomic theory. We've gone from John Dalton and his basic atomic theory, where he imagined atoms were just small hard spheres with no structure. We then jumped to J.J. Thomson, who gave us the raisin-bun model of the atom after he discovered electrons using his cathode ray experiment. Then we moved on to Ernest Rutherford and his solar system-like model of the atom with a nucleus at the center, and he said that electrons were found outside that nucleus like planets around a sun. And that brings us to the last model of the atom that we look at in grade 11 chemistry, Niels Bohr, the Bohr model of the atom. Bohr is going to add a little tiny detail to Rutherford's idea. In the Bohr model of the atom, we still have a nucleus at the center, and the electrons are like planets orbiting the nucleus. The difference, though, is that in the Bohr model, there are only certain orbits that are allowed for these electrons, only certain energy levels that they're allowed to have. All right, now in the Bohr model, the closer to the nucleus you are, the lower the energy of the electron. And the further away it is from the nucleus, the higher the energy of the electron would be. When an electron has more and more energy, it's able to fly further and further from that nucleus, which is attracting it, right? The protons in the nucleus are attracting the negatively charged electrons. In the Bohr model, he uses the letter N to describe the energy levels, or the orbits, and he gave them whole number values for N. So he said N equals 1 was the first or the lowest energy orbit. N equals 2 was the second lowest energy orbit. N equals 3, N equals 4, all the way up to N equals infinity. So his model is sometimes called a quantum model because he restricted the electrons to only certain allowed energy levels. All right? Rutherford's model said electrons orbit the nucleus. Bohr's model adds that they only occupy certain energy levels, certain orbits. Right, now if I'm going too fast for you, I hope you're taking good notes. Pause the video here and write down what you need to before we go on. In the Bohr model of the atom, so we have a nucleus. Here it's pictured as little yellow protons and orange neutrons. Normally we wouldn't draw it like that. And then we have orbits, in this case 2 orbits. The first orbit there would be the N equals 1 orbit, the first energy level, and the second orbit is the N equals 2 energy level. Now in the Bohr model, we'll come back in grade 12 chemistry to revisit this, but let's just point out a few important details. In the first energy level, the maximum number of electrons that can be held there is 2. All right, so the first orbit, the first energy level, can hold only 2 electrons. If an atom has 1 electron or 2 electrons, that's where they will be in that first energy level, that first orbit. But if it has 3 electrons or 4 electrons or 5 electrons, then we'll put the first 2 electrons in that first orbit, and we'll put the next electrons in the second orbit, the second energy level. The second energy level, the second orbit, can hold up to 8 electrons. When it's filled, we'll move on to the third energy level. Now technically, the third energy level, the third orbit, can hold up to 18 electrons, but we will never draw one that has that many. We'll draw only up to 8 electrons in the third energy level. But technically it can hold up to 18. A general formula is if you're in the nth orbit in an atom, there can be 2 times n squared electrons in that orbit. For example, when n is 1, the first orbit, 2 times 1 squared, you can have 2 electrons there. When n is 2, 2 times 2 squared gives me 8 electrons in the second energy level. When n is 3, 2 times 3 squared gives us 18 electrons in the third energy level. But again, we'll never draw a Bohr model of the atom like this with more than 8 electrons in the third energy level. So let's draw a Bohr diagram for carbon-14. It'd be helpful if you had a periodic table with you. So if you want, you can pause the video and open up a periodic table along with this. The first thing you want to do is draw a nucleus. So here I've drawn a little circle. We look on our periodic table and we notice the atomic number for carbon is 6. So because its atomic number is 6, we know that means it must have 6 protons in the nucleus. When we said carbon-14, the 14, of course, is the mass number. We know that from our discussion of isotopes. The mass number is the total number of protons with neutrons. And since we know we have 6 protons, the atomic number was 6, we can say 14 minus 6, it must have 8 neutrons also. So in my nucleus, I wrote 8 neutrons. Now you remember that the number of protons, which are positive, will equal the number of electrons, which are negative, in a neutral atom. So if we have 6 protons, we must also have 6 electrons. The protons are positive, the electrons are negative. Now where are those 6 electrons? Well, start by filling the first energy level. Put the first electron wherever you like in that first orbit, and then draw a second electron opposite from the first one. I've drawn the first electron above and the second electron below the nucleus, okay, but just put them opposite from each other. So we have 4 more electrons to place. We had 6 total, we've already used 2. So we need to put 4 more electrons, and those are going to go in the second energy level, the second orbit. The first electron you can put wherever you like in the second energy level. Let's put one here. Now we're going to move around in 90-degree increments, or at the points of a compass, if you like. So there's the first electron, here's a second electron, a third electron, and there's the fourth electron. We're now done. So there's 4 electrons in the second energy level, 2 electrons in the first energy level. There's the Bohr diagram of carbon-14. Try it again, this time for oxygen-15. If you'd like to pause the video and see if you can do it yourself. All right, so we glance at a periodic table again, and we notice that the atomic number for oxygen is 8. So that tells us that there's 8 protons in the nucleus. 15, again, was the mass number. Whenever you're doing this, use these terms in your head or explain it to a friend by actually using the vocabulary. That way you'll learn it, you'll remember it. So the 15 is my mass number. It's the number of protons and neutrons. So if we take 15 and we subtract the 8 protons, we get 7 neutrons, which are also in the nucleus. Since we have 8 protons, the 8 protons are positive, we need 8 electrons to go with that. The first 2 are in the first energy level, the first orbit. Put one wherever you like in that orbit, and put the second one opposite from it. So we have 6 more electrons to go, and remembering that the second orbit can hold up to 8 electrons, we can put all 6 in the second energy level. So here we go. Put the first one wherever you like, and then the second one 90 degrees away, and then 90 degrees away, till we have like that 4 electrons in that second energy level. We need to put 2 more. So now we'll start pairing them up. So there's a 5th, and there's a 6th electron. All right. Now just a quick piece of vocabulary. The electrons that are in the outermost energy level are referred to as valence electrons. Those are the electrons in the outermost, or if you prefer, the highest energy orbit. So here we would say that oxygen has 6 valence electrons, right? There's 6 electrons in the second energy level. So the quantum model of the atom, Bohr's model of the atom, has been an evolution. You don't really need to write much of this down. If you just want to skip over this, that's fine. As I mentioned earlier, Dalton's model morphed into Thomson's model, a raisin bun model. Rutherford's idea that there's a nucleus and the electrons are orbiting it. Keep in mind that these pictures are totally incorrect in terms of their scale. The nucleus of the atom, recall, would be the size of an ant if the atom were as big as a football stadium. So if this was the atom, the nucleus shown here is way, way, way too big. But that's just so that you can see it. Bohr's model has those electrons arranged in energy levels. When we get to grade 12 chemistry, we'll come back and we'll throw all those models out, including the Bohr model, and we'll revisit it with what's called the quantum mechanics model of the atom, where electrons are no longer viewed as negatively charged particles. That model of the atom is going to make your brain hurt. So we leave that to grade 12 chemistry. So for now, we're going to stop there, and in grade 11 chemistry, we'll deal only with the Bohr model of the atom. Keep in mind that any model, all of these are models, are by definition not true, right? A model is not true. A model is a representation of what we think is true. So it's like a simplification. The Bohr model is a pretty good simplification, but in grade 12 chemistry we learn a better one, the quantum mechanics model. Now sometimes instead of drawing Bohr models, which can be tedious to draw those orbits and the electrons like that, instead we draw something a bit simpler called an energy level diagram. Make sure you know which is which. If you're asked to draw a Bohr model of the atom, that's what we just did. If you're asked to draw an energy level diagram, that's what we'll see here. So instead of orbits, we're going to draw little energy levels to represent to show where the electrons are found. So let's draw one here for a neutral fluorine atom. Glance at a periodic table. Fluorine is element number 9. Right? Its atomic number is 9. So when you draw an energy level diagram, you write the symbol of the element, in this case fluorine. Right above it will indicate that it has 9 protons. That's because its atomic number from the periodic table was 9. So it has 9 protons. That means it must also have 9 electrons. Now the first 2 electrons can go in the first energy level, the first orbit, so we draw a little line above the 9 protons and we'll say that there's 2 electrons there. So that means 2 electrons are in the first energy level. We have 9 electrons total, so we have another 7 electrons to go, and the second energy level, the second orbit, can hold up to 8 electrons, so we can put these next 7 electrons into the second energy level. And there we go, that's it. There's the energy level diagram for fluorine. Notice it tells you the same information as a Bohr diagram. The nucleus with 9 protons, 2 electrons in the first orbit, 7 electrons in the second orbit. And just a reminder that the outermost electrons, the ones in the highest energy level, are called valence electrons. Arguably, those are the most important electrons for chemistry. In chemical reactions, it's the valence electrons which are involved in the reaction. In this case, fluorine has 7 valence electrons.